This is Euclid Book 10, proposition number 64. After this proof, there'll be one more with this diagram, and then we'll move on to something else. The square on the side of a rational plus a medial area applied to a rational straight line produces as breadth the fifth binomial. Let AB be the side of a rational plus a medial area. That's this line right here. Divided into its straight lines at C, so that AC is greater than CB. So this length is greater than this one. Let a rational straight line DE be set out. That's this one right here. And let there be applied to DE the parallelogram DF, which is this whole rectangle right across here. And the area inside of this whole rectangle is going to be the same area as this one right here. And it's going to produce this line DG, which is going to be the breadth of this whole area. I say that DG is the fifth binomial straight line. Let the same construction as before be made. Since then, AB is the side of a rational plus a medial area divided at C. That's this line right here. Therefore, AC, CB are straight lines incommensurable in square. So this line and this line are incommensurable in square, which make the sum of the squares on the medial, but the rectangle contained by them rational. Okay, so if you add up these two areas, that's going to be medial, but if you have this area right here, it's going to be rational. This is by Euclid Book 10, proposition number 40. Since then, the sum of the squares on ACCB is medial, therefore DL is also medial. Whole area right here, this plus this together is going to be medial, so that DM is rational and incommensurable in length with DE. Okay, this line is rational and it's incommensurable with this line. That's by Euclid Book 10, proposition number 22. Again, since twice the rectangle ACCB, that is MF, is rational, so if you multiply this times 2, you get a rational area. And this area right here is going to be the same area as this plus this. All of this is going to be twice. This times 2 will be all of this area. Okay. Therefore, MG is rational and commensurable with DE. Okay. Why is MG commensurable with this? Mainly because this is commensurable with this, and since this is exactly the same length as this, then therefore this is commensurable with this. That's why. By Euclid Book 10, proposition number 20. Therefore, DM is incommensurable with MG. This length and this length are not commensurable. This is by Euclid Book 10, proposition number 13. Therefore, DM, MG are rational straight lines commensurable in square only. So, the only time that these two lines are commensurable is if you were to make a square out of this and a square out of this. Then the two square areas would be commensurable. Otherwise, these two lines here are not commensurable. Therefore, DG is a binomial. This whole line is a binomial. This is by Euclid Book 10, proposition number 36. I say next that it is also a fifth binomial straight line. For it can be proved similarly that the rectangle DKKM, that's this one right here, is equal to the square on MN. Okay, so if we were to take the length of MN and make a square out of it, this area would be the same as this. And that DK is incommensurable in length with KM. This length and this length are incommensurable. Therefore, the square on DM, this whole square right across here, is greater than the square on MG, the area of this, the area of this square. This square is greater than this square. How much bigger is it? By the square on a straight line incommensurable DM. So basically the area of DE. And DM and MG are commensurable in square only, and the less MG is commensurable with the length of DE. So this line here is commensurable with this. Therefore, DG is a fifth binomial. Alright. That's the end of that proof. We have one more to go with this diagram, and then we can move on to something else. I will tell you more in a future video, so I want you to stay tuned.